In my last series of lectures, I went through the basics of vector mathematics. Understanding vector mathematics is necessary to begin to describe mechanics, the science of motion. Now, mechanics itself is divided up into two parts. There is, first of all, what is called kinematics. Kinematics is concerned with the mathematical description of motion. You'll be introduced to kinematics in chapters 2 and 3. Now, motion is perhaps the simplest of all physical phenomena. But as you'll discover in kinematics, mathematically describing the following, literally something as trivial as this, is actually mathematically difficult to do. You'll be introduced to kinematics in chapters 2 and 3. In chapter 2, we'll take a look at one-dimensional cases, and in chapter 3, we'll look at two-dimensional cases. We actually, by the way, have already done a little bit of chapter 3, and the reason for that is because the basics of vector mathematics is introduced in chapter 3. In just a few moments, however, we're going to jump back to chapter 2 to take a look at one-dimensional cases. Before I do, however, the second half of mechanics is what is called dynamics. Dynamics is concerned with understanding the causes of motion. For those of you enrolled in Physics AB, you'll be introduced to dynamics in chapters 4 and 5. For those of you enrolled in Honors Physics AB and AP Physics C, you'll be introduced to dynamics in chapters 4 through 6. But for now, we jump back to chapter 2 and we begin to take a look at one-dimensional kinematics. Kinematics begins with a series of definitions. The first of those definitions is actually something that we have already described, and that's position. Position is perhaps the simplest of all vector quantities to describe. It's the first definition that is necessary in kinematics. When we are talking about one-dimensional motion occurring along a number line, say horizontally, we always use the letter X to denote position. Now, it is technically speaking a vector quantity, but notice that I am not drawing the vector symbol above the letter X. And the reason for that is because the full vector notation involving I hat and j hat unit vectors, for example, is considered redundant when you're just talking about a one-dimensional case. Because in a one-dimensional case that occurs horizontally along a number line, we could simply denote to the right-hand side as positive and the left-hand side as negative. So we just use plus and minus signs to denote those directions, and then therefore the full vector notation is considered to be redundant. Now let's say that we're taking a look at an object, and we note its position when we first begin to look at the object. That's referred to as the initial position. The initial position is drawn as the letter X, but then we write a little subscript 0 next to it like so. This is pronounced X naught. X naught describes initial position. And then some time interval goes by, and then the object then, with respect to an origin, has a final position. That final position is always written simply as X. This then means that over this time interval, the object underwent a change in position. Whenever we describe the change in a quantity, we always use the Greek symbol delta. Delta x in this case refers to change in position. Now, whenever you describe the change in a quantity, the change in the quantity is always the final value minus the initial value. So then therefore, if we're talking about change in position, delta x is equal to the final position x minus the initial position x naught. Now, because these are vectors, this then means that the tail to tip method of vector addition occurs in this algebraic expression. Here's the easiest way, rather, to see how the tail to tip method works. We'll see this in a specific example a little bit later on. Okay, the easiest way to see the tail to tip is to take the initial position x naught and move it to the other side of the expression. So then therefore initial plus change is equal to final, like so. We'll see that in a specific example in just a few minutes. Now, as I've described here, the object's change in position, I've mentioned a time interval. So then therefore we can immediately ask the following question: exactly what is meant by time? Well, answering that question, it turns out, is actually at the very forefront of theoretical physics today here in the early 21st century. Exactly what is meant by time. That's way ahead, however, of where we are here in this class. So then therefore, for our purposes, you can think of time as just simply something that clocks measure. That's good enough. Okay, now, next, we get to two defined quantities where the questions themselves, the words that we use rather to describe these quantities, we somewhat use interchangeably in everyday language. And those are the words speed and velocity. Speed and velocity, however, are not the same thing. They do have distinct mathematical meanings that are different from each other. Okay, first of all, we have what is referred to as average speed. Okay, average speed is written first of all in the following way. We write the letter V, there's a little subscript S next to it to denote speed, and then we put a bar symbol above. The bar symbol in mathematical notation means average. Now, by definition, and incidentally, by the way, whenever you see me write an extra slash associated with an equal sign, it means by definition. By definition, average speed is distance divided by time. We usually just simply write this as d over t. Distance and time are both scalar quantities. There is no direction associated with distance. It's just a magnitude. In other words, therefore, it's a scalar. So if I have here two scalar quantities, one divided by the other, this then means that average speed is a scalar. Okay, now distinctly different from that mathematically is what is called average velocity. Once again, we tend to use the words speed and velocity interchangeably in everyday language. They're not the same thing. Okay, average velocity is denoted as V. There's once again a bar symbol above for average, and by definition, this is equal to change in position divided by change in time. Notice that the numerator of this expression, change in position, is a vector quantity. Therefore, this then means that average velocity is a vector. Let's immediately illustrate the difference between the two, that is average speed and average velocity, with an example. So at this point, go ahead and copy down into your notes the first of today's examples. I'm going to erase the board and then read the example from my screen in just a few moments. Notice that the example is just an extension, if you will, of one of the examples that we looked at for basic vector mathematics. Let me begin to read it to you. A student walks 5 meters to the right and then 10 meters to the left in a total of 60 seconds. In part A of the problem, what is the student's change in position? Change in position, by the way, is also sometimes known as displacement. Let's assume, by definition, that the person starts at the origin. So then, therefore, the student's initial position, x naught, is equal to 0. And then the person walks 5 meters to the right and 10 meters to the left. This then means that after 60 seconds, the person's final position, x, is -5 meters. And now here in part A of the example, we calculate the displacement. That is the change in position. That's final minus initial. So then therefore, this simply ends up being -5 meters. Here's then how we represent this algebraic expression on a number line by using the tail to tip method. Okay, so here's a number line now to represent position in terms of meters. Here's the origin, and then 5, 10 to the right. Let me give myself some room here. 5, 10 to the left. And then we have the student's initial position being equal to 0. How do you draw a vector that has no magnitude? You just simply draw it as a point, like so. So here's x naught. And now to show the tail to tip method, what we do is we take the initial, add to it the change to then get the final. So now what I have to do is place the tail of the second vector, delta x, this -5 meters, at the tip of the first vector, x naught. So then therefore that's drawn in the following way. Right here is the delta x vector, like so, of -5 meters. So pantomiming this then looks like the following. The initial plus the change is now equal to the final position x. That's this -5 meters here. I'll go ahead and draw that vector below the number line like so, such that we can then see it. So initial plus change is equal to final, like so. So that's how you show the vector addition of this expression by using the tail to tip method. Okay, now let me reveal the remainder of the example. Okay, now in part B of the problem, we calculate the total distance traveled. The total distance traveled is just all of the lengths, if you will, of the vectors, the magnitudes themselves added together. So the person then therefore walked a total distance, we'll call it D, of 15 meters. Like so. And now in parts C and then D, we get to average velocity and average speed. So first of all, in part C, the average velocity v bar, which is change in position divided by change in time. So we have the change in position, -5 meters, divided now by the change in time, which in the problem is given as 60 seconds. Now let me go ahead and divide this out on my calculator. 5 divided by 60, and rounding it off a little bit, this is about -0.083 or so, like so. Now how do we then write down the units? Well, recall that unit symbols behave like numbers. So we're taking meters here and dividing it by seconds, and we just leave it as such. The units of velocity are meters per second. Now this is a vector quantity, so then therefore I should be able to draw it on a number line. Can I draw the average velocity vector, however, on the position number line above? No, and the reason for that is because that number line represents position. I have to have velocity with its own number line. This is, by the way, sometimes referred to as velocity space. So right here is now another number line representing velocity in terms of meters per second. Here's the origin, and then here to the left-hand side is 0.083 meters per second. So then therefore on this number line, the average velocity vector v bar looks then like this. Like so. And now illustrating the difference between average velocity and average speed, let's finish the example here with part D. So in part D, we're now calculating average speed, which is just distance divided by time. It's 15 meters divided by the same 60 seconds. 15 divided by 60 is just 1/4 or 0.25 meters per second. Once again, the units here are meters per second. The units of speed and velocity are in fact the same. Now, a problem such as this is obviously very easy to perform, and the reason for that is because we're just doing some simple algebraic manipulation with basic numbers. Calculating this value and calculating this value is obviously easy to do. But notice that these values don't really tell you all that much. They don't tell you, for example, what happens at an instant in time, literally a time interval of 0 size. So even though these quantities are easy to calculate, they are then therefore not a complete description of the motion. So then therefore, what good are they? Okay, let me do some erasing. Okay, so summarizing what I just said a moment ago, note that the average quantities are easy to calculate, but they do not describe what happens at an instant in time. Literally a non-measurable amount of time. So then therefore, they are not a complete description of the motion. So what good are they? Well, they do lead us to what's important, a description of what is referred to as instantaneous velocity. Here's how we arrive at this next definition, at this description. Okay, I'm going to do a little bit of erasing here. Make sure that you have this copied down, however. Let's say that we construct the following graph, the position of an object as a function of time. So time along the horizontal axis and position x here on the vertical axis. And so let's say that an object is undergoing some sort of one-dimensional motion and its position as a function of time traces out some sort of smooth curve polynomial, some sort of function, for example, like so. And now what I'm going to do is I'm going to take a look at two moments in time. Let's say that we start the clock, for example, right here at this moment in time. And then therefore on the position axis, the object has right here an initial position x naught. And then some time interval goes by, like so. So here's the final moment in time. And then therefore here on the position axis, the object then has a final position x. The time interval itself, delta t, is this space here on the time axis. What I'm going to do is I'm going to connect these 2 points with a line. This line is sometimes referred to as a chord. It's also sometimes referred to as a secant line. So let me do that like so, here with this color. Obtaining this line. Now let me go ahead and calculate the slope of this line. Now recall, of course, that slope is rise over run. So in this case, first of all, the run. The run, you'll notice, is the time interval delta t. But now take a look at the rise. The rise is the difference between these two values. It's the final value of the position minus the initial value. So right here, the rise is the change in position delta x. Notice that this quantity here, change in position over change in time, is average velocity. So the average velocity, as we saw in my previous algebraic example, is easy to calculate, but it didn't tell us what happened at an instant in time. Instead, it tells us what happens over a broad time interval. Let's say that I wanted to know exactly how the position of the object is changing right here at this instant in time. What I have to do is I have to take this quantity, take the time interval, and make it infinitesimally small. This is referred to as taking the limit. If I now make the time interval infinitesimally small, then the diagram, the graph, looks like this. Okay, so same red polynomial function as before, like so. But now we take a look at this instant in time. In order to describe exactly how this red polynomial describing position is changing at this instant, we're once again finding the slope of a line. But in this case, it's a line that is tangent to the curve locally at that point. In other words, the line only intersects this point here on this red polynomial. I'll just draw that very simply, like so. Like this. This line right here in green is referred to as a tangent line. The slope of that line describes exactly how the position is changing at that instant. How do I calculate it? Well, what I am calculating here is now referred to as instantaneous velocity. Instantaneous velocity is now just referred to as v. It's the same thing as the quantity above, the average velocity, but now what we've done is we've taken the time interval, delta t, and we've made it infinitesimally small. This is called taking a limit. That is, we take the limit as the time interval approaches 0 of change in position divided by change in time. This quantity here is known as a derivative. Now, for those of you enrolled in Physics AB, which is an algebraic-based course, we will not actually calculate any derivatives. And then therefore, the notation that you will see for a derivative, just describing it qualitatively in this manner, is this expression here. However, for those of you enrolled in Honors Physics AB and in AP Physics C, we usually describe instantaneous velocity in the following way. The derivative of position with respect to time. This is notation that you'll see for this derivative here in a physics course. Now, if this is instantaneous velocity, what is instantaneous speed? Here's how we illustrate the difference between the two. Okay, now what I'm going to do here at my desk is I'm going to picture the calculator here, like so, as an origin. And then what I'm going to do, much like in the example that we just completed, is undergo some sort of displacement. Let me, for example, do the following like so. I'm going to walk in this direction, and then walk to here. Now, right here is my change in position vector, delta x. And then this plus this is the total distance that I traveled. Notice that the magnitude of my change in position vector and the total distance that I traveled are two different numbers. So like in the last example, I would then calculate different numbers for the average velocity and the average speed. But watch what happens to the magnitude of my change in position vector and the total distance traveled if I now take the time interval and make it smaller. So now I'm going to do the following. We'll start the clock here and then stop. Like so. So right here is my change in position, and then right here is the total distance traveled. Notice that those two numbers are still different from each other, but they are now closer together. So then what happens with those two numbers in literally an instant in time, a non-measurable amount of time? Well, right there was the distance that I traveled. It's infinitesimally small. And right there is my change in position vector. It's also instantaneous, or also infinitesimally small. Because those two numbers are infinitesimally small, this means that they're the same thing. So instantaneous speed then therefore is nothing more than the magnitude of the instantaneous velocity vector. Here's how you can easily differentiate between the two. Let's say that you're in a car that's traveling at 60 miles per hour down the freeway, and you look at your speedometer. What is your speedometer giving you? Your speedometer. Well, it's giving you your instantaneous speed. So your instantaneous speed would be, say, 60 miles per hour. However, let's say you're driving to the north on the 405 freeway. So then therefore you would say that your instantaneous velocity vector is 60 miles per hour to the north. That's the difference between the two. So the average quantities, average velocity and average speed, as we've seen, don't tell us all that much, but they lead us to what is important. They lead us to a description of instantaneous velocity. However, in order to determine instantaneous velocity, it literally means taking a quantity and dividing it by 0. So then therefore, differential calculus is necessary to describe motion. This flummoxed mathematicians for more than 2,000 years. As far as more than 2,000 years ago, the ancient Greeks tried to formulate a mathematical description of the following, and they couldn't. And the reason why they couldn't is because what it requires is literally taking a quantity and dividing it by 0. That took mathematicians nearly 2,000 years to figure out. The problem was actually solved more or less simultaneously by two people at the same time. Gottfried von Leibniz, a mathematician in Germany, and Isaac Newton in England. We still use today, by the way, the descendants of Leibniz's notation when it comes to basic calculus. That's what you're beginning to see here, however, but in a physics context. Okay, I'm going to conclude this portion of the lecture as part 1. I'll get to part 2 in just a few moments.